Let's explore a problem in heat transfer known as a semi-infinite solid. In this situation, we've got some solid. There's a coordinate direction x to the right, coordinate direction y upward, and a coordinate direction z coming out of the screen. Now the dimensions y goes infinitely far up and down, and the dimension z goes infinitely far into and out of the screen. The parameter x, though, the dimension x, starts at x equals 0 and only goes infinitely far to the right. It doesn't go anywhere to the left. And we're trying to figure out the temperature of our solid as a function of both x and a function of time. Now in real life, there's no solid that's actually infinitely far, but this does have applicability when we're just trying to examine the heat transfer near the surface of our solid. And now let's simplify the heat diffusion equation. Because the solid runs infinitely far up and down and infinitely far into and out of the screen, we'll delete those two terms. And in addition, the solid has no heat generation. However, because this is an inherently transient problem, we'll leave the term on the right-hand side. We'll also assume that the thermal conductivity K is not a function of temperature, so we'll pull it out of the first term. And then we'll use the definition of our thermal diffusivity, alpha, which is equal to K over rho C P. To simplify this expression, we've got alpha times the second derivative of temperature with respect to x is equal to the partial derivative of temperature with respect to time. So this now becomes our governing partial differential equation. Note that it's second order with respect to temperature and first order with respect to time. And that means we need one initial condition and two boundary conditions. Our initial condition is that the temperature is equal to T naught at time equals 0 for all values of x. Our first boundary condition will also be that T is equal to T naught, but this time at x approaching infinity. So very deep into the solid, T is equal to the initial temperature. And this applies for all time. And we can do a few things for the second boundary condition. However we specify the second boundary condition, it's going to apply at x equals 0 also for all time. We can do things like specify the temperature at x equals 0. We could specify the flux at x equals 0. We could say that there's a convection occurring at x equals 0. Maybe there's air or water or some other fluid on the left-hand side where we have a heat transfer coefficient and some T infinity. We can also do things like have an oscillatory flux on the left-hand side such that the wall or the solid will heat up and cool down periodically over time. In this case, let's start with probably the simplest case in which we're fixing the temperature. We're going to say that T is equal to Ts, some constant temperature, at x equals 0. So to solve this partial differential equation, subject to the initial conditions and the two boundary conditions we've specified, we can use what's known as a similarity variable to arrive at an expression for the temperature as a function of x and time. The solution isn't easy to interpret at first glance. Here, ERF stands for the error function. In this case, we're taking the error function of x, the position, divided by the square root of 4 times the thermal diffusivity times time. This is the definition of the error function of some variable eta. It's an integral that can't be solved analytically, so as a result you often go to a table of values, or it's available in most software such as MATLAB or Microsoft Excel. And this is a graph of the error function. We find that the error function has a value of 0 at eta equals 0. It asymptotically approaches 1 for large positive values of eta, and asymptotically approaches -1 for large negative values of eta. By comparing the temperature profile to the graph of the error function, we can see for large values of the error function, large values can occur at large values of x, for example. So if we're deep into our solid. In that case, the error function asymptotically approaches 1, and we'll find that T is equal to T naught in that limit. Which makes sense because if we're infinitely far into the solid, there's not enough time for heat to diffuse into the solid that far. Another way to make this value very large is to examine short periods of time. And in that case, a short period of time, there isn't enough time for the heat to diffuse even through short distances. And we'll find that T is equal to T naught at short distances into the surface. At the other extreme, for x equals 0, the error function of 0 is equal to 0, and we'll find that T is equal to Ts, the surface temperature. That applies for our boundary condition at all points in time. We can also examine the flux, which is by way of Fourier's law is -k times the partial derivative of temperature with respect to x. So differentiating our solution for temperature with respect to x will result in a flux that's equal to this expression. One thing we can note is that deep into the solid, if we have large values of x, the flux is equal to 0 because the heat hasn't penetrated that far yet. We also observed at large values of time, the flux decays to 0, and then in that case, most of the solid has already warmed up to the surface temperature, and then in that case, there's no temperature gradient and the flux is 0. In this problem, I want to explore the flux at x equals 0, so the flux at the surface, and in that case, if x is equal to 0, this exponential drops out. And this indicates that the thermal flux at the surface decays as time progresses. So I'm going to show you a simulation of this problem, but there's a few things to keep in mind. The first of which is that the temperature at x equals 0 is going to remain constant over time. We're also going to observe that for large values of x, T will asymptotically approach the temperature T0 deep into the solid. We'll also observe that for long periods of time, the temperature deep into the solid will approach the surface temperature. After a long period of time, the heat will diffuse deeply into the surface. And then lastly, we're going to observe the flux at the surface being infinite when time is equal to 0, and that's because there's a step change in the temperature. The temperature will immediately go from Ts to T0 over a length that's equal to 0. And then finally, over a long period of time, when the semi-infinite solid becomes more uniform, our flux will asymptotically approach 0. So here's the start of the simulation at time equals 0. The first thing you're looking at the top is the semi-infinite solid, and I'm using a color scale with blue representing T0, which I've set to 20 degrees in this simulation, and it will progress through white at 150 degrees into red at the surface temperature, which I've set to 300 degrees. The second graph is the temperature as a function of depth into our semi-infinite solid. Here I've set at time 0 the temperature, well, we fixed the temperature at 300 degrees for all periods of time, and at time 0 the temperature drops from 300 degrees C down to 20 degrees over a distance of 0. Once the simulation progresses, the simulation will show the flux decaying from infinity down to 0 over a long period of time. So watching the simulation, this white value represents a temperature of 150 degrees, red represents temperatures higher than that, blue temperatures lower, and we see this asymptotic decay in the flux as time progresses. And this flux I'm showing is the flux at the surface. So one thing to pay attention to is the temperature gradient, how that relates to the flux. So here I've restarted the simulation. We can play it a little bit more slowly. I can mouse left and right to change the time. What I want you to really compare is the slope, the gradient here at x equals 0. Compare that to the flux. Here we have a very large negative temperature gradient. The temperature is decaying from 300 degrees to 20 degrees over a very short distance. However, as time progresses, that temperature gradient becomes smaller and smaller. The distance over which the temperature decays from the surface temperature to T infinity is increasing over time as the heat is diffusing into the solid. So over long periods of time, we see the temperature gradient becoming smaller and smaller, and at the very surface we see the temperature is more uniformly at 300 degrees. Also, pay attention to the fact that we're obeying the two boundary conditions. The temperature is held at the surface temperature of 300 degrees C, and the slope dt dt is equal to 0 deep into the solid for all periods in time.